guys, welcome to Learn Extra Live. You grade 12s have all been waiting for this. It's finally your turn, and today we're doing physical science with Phil, guys. It's going to be such an amazing show. As you know, I'm Katleho, and guys, I need you guys to chat to me today. I need you guys to say all you need to say and ask as many questions as you need to ask on our Facebook page. That's facebook.com/learnextra, and our Twitter handle is @learnextra. These are the platforms for you guys to basically just engage with us, guys. Engage with Phil today. Today, Phil, do you want to let us know what we'll be doing there?
Absolutely, Kat. Well, today we're going to be taking a look at work and energy, and as you can see on the screen behind me, we're going to be doing some more virtual practice.
Awesome.
I'm going to be showing you some swinging pendulums.
Awesome,
So,
Phil.
okay.
Awesome, guys. So you guys know what to do. You know Phil's virtual thingies are really awesome. So if your friends aren't on the page yet or aren't watching yet, please give them a shout and tell them that Learn Extra Live is now on with physical science, and we need you guys to join us. Thank you to Macmillan for bringing us such an amazing show, guys. We really enjoy being here as much as you guys enjoy being here. So please make sure today is one of the best physical science lessons for you guys. I know you guys need it, and I know you guys have questions. So send them to me right this moment. Over to you, Phil.
Thanks so much, Kat. Well, as you can see behind me, we're going to be using one of the FET simulations. Kat's going to be posting up one of the simulation websites, and you guys, I want you to surf over here. If you've got a PC in front of you, please, guys, I want you playing around with this. I want you fiddling around with this particular simulation. This one is called Energy Skate Park. Okay, so guys, Google FET, P-H-E-T, so phet.colorado.edu. And these guys have made these amazing apps, and they're just for free, guys. They are up there for free, and I want you to surf over here and start playing around with the Energy Skate Park. Okay, but now before we get too tied up and this guy busy enjoying himself skating, let's get down to business. Let's start taking a look at today's topic, and that is work and energy. Okay, well, most of you guys have done a little bit of energy, and remember your energy from grade 10. So we're going to focus a little bit less on the energy and a little bit more on the work, and then eventually at the end we're going to link them up with the work-energy theorem. So now all this is good and well, but guys, if you've really cottoned onto this idea, notes, guys, they're on the page, and the really nice thing about this is that most of the examples which I'm going to be working through are in the notes. You don't have to scribble and go mad making your own notes. Guys, they're available, they're for free, they're on the web. Okay, so here we go, work and energy. Let's take a look at what's up today. Okay, well, there's a couple of things that I want to make sure that people understand. Okay, we want to make sure that we know that objects have got potential energy as a result of position, and kinetic energy as a result of motion. Guys, that's a little bit of revision of grade 10. So here we go. We're talking about potential energy and kinetic energy. So those are the two types of energy which an object can have in terms of mechanical energy. We're going to take a look at that guy skating on his skateboard in a moment, and we're going to try link it up with a pendulum, which I've got linked up here in the studio, and we're going to try see how mechanical energy actually works. Now, here's the thing that I want you to focus on. We need to learn that work is the transfer of energy from one form into another. There we go. So transfer of energy. And that, in fact, is the definition for work. Guys, I need you to know what it is before we start working with it. Excuse the pun. So we've got equations to describe work and energy. Well, some of those will be old, some of them will be new. I want you to work with me, work slowly, work through the stuff. And guys, work and energy is actually such a great section once you understand how to work with it. Okay, so it says use work and energy concepts to solve exam time problems. Guys, I want to get to this as quickly as possible. A lot of you guys are requesting and you're saying, Phil, please help me with exam type questions. So work and energy. Now in terms of the work energy theorem, guys, matric, that's the new stuff. That's where we're focusing our attention today. All right, let's jump straight into this. Let's start taking a look at some of the types of energy that an object can actually have. So I'm holding this pen, I've got a pendulum over here, I'm a human body over here. All of us have internal energy. I just want to start picturing the types of energy which can actually take place in a body. So I've just drawn up a brief flow diagram. And guys, please don't scurry to write this all down. I just want to plant a picture inside your brains and say, okay, well, an object can possess energy. So I've got energy, you've got energy, we ate food this morning to make that this way. So I gave myself some internal energy. Now that internal energy can go multiple ways. Well, I know that you guys have got a little bit of a temperature, or at least a pulse. I'm hoping you guys do. Okay, otherwise you're dead. But heat and chemical is where most of our energy actually goes into. So I eat up this food and it gets stored as chemical potential energy. Any of the life sciences students will know that it gets stored as glycogen and as lipids inside my cells. Okay, so heat is the other byproduct of my metabolism. I eat food, I give off heat, I store some chemicals. But here's where the rest of my energy goes. So let's take a look at this flow diagram and let's see what this mechanical energy actually is. So the internal energy came from the food. It went two ways. So the one way was to store it as chemical energy inside my cells, hopefully not storing too much, and then giving off a little bit of heat. If you feel your forehead, you can feel your temperature very nicely, hopefully not too much. And here's where I'm going to focus my attention here. Okay, mechanical energy. Mechanical energy is the stuff that we're going to be dealing with in a moment. Guys, I want to do a little bit of quick grade 10 revision. Okay, the two types of energy which I'm really going to focus on here, kinetic and potential energy. These two give me mechanical energy. Now guys, if you start moving around your muscles and if you start walking around, standing up off the couch, getting down, writing with your pen, guys, you are investing in your mechanical energy of your body. I can give my body kinetic by running or moving something, and then potential. Now, I've already got potential energy. I'm on the second floor of a building. I have the potential to go down again. Hopefully, I don't release that all at once, okay? But
I don't think you're that strong.
okay, well, look, I mean, I could jump off the building, but,
Oh,
you
you
know,
can.
we'd rather carry on with the lesson. Okay, but kinetic energy and potential energy. Guys, these are formulas which are lifted straight off one of your past papers. That is how they've been given. Now, some of the confusion in the textbooks say, do I use K or do I use EK? Well, guys, you can use both because they're both on your formula sheet. So K or EK describes kinetic energy. That is the energy of movement. Switching over to potential energy, they've introduced this really strange symbol, which is U. And it's also EP, so energy potential. Now, guys, I just want to point out some very important things about this. Okay, now in my kinetic, a lot of people are saying, well, I just chuck in a mass, you know, whatever grams I got, just throw it in. Guys, please, the units are very important. Kilograms on my mass, my velocity, don't forget, that is meters per second. And when we jump onto our potential over here, we've got M, and that is also in kilograms. Now, guys, please, G. It's very, very important that you all use the same G. So G is 9.8 meters per second squared. And you're saying, where did I get that from? Well, guys, look on your information sheets. Your information sheets are there for free. I've put a link on my notes to find those past papers. Guys, please, G is available. I want you to make sure that you're very familiar with your formula sheet, where to find all the constants. So there it is. My mass in kilograms, G is 9.8. And then H, which is something quite new, which is my height. And that's measured in meters. Okay, but at the moment, we're still dealing with grade 10 work. What I'm going to do now is I'm going to ask you to come with me, and we're going to start taking a look at something called a pendulum. So what I'm going to do is I'm going to ask my cameraman here to follow me over to my experiment, and we're going to start taking a look at those two types of energy and how they change and the concept of work. Okay, guys, come with me. So what we're going to do now is I'm going to turn your attention to this thing. Now, I'm pretty sure you know what I'm about to do with it. This thing is a pendulum. All it does is it swings. Now, you might say, okay, well, Phil, what's the big deal about that? Well, the whole idea behind this is that this is a mechanical energy conservation device. And I know a whole bunch of you are saying, whoa, okay, what have you just said? Okay, now I want you to take a look at this piece down here at the bottom. I've got a mass piece down here at the bottom. This is weighted to around about 100 grams. Now, if I want to invest some energy into this, what I told you earlier was that I had to do work on this object. Anytime you want to give energy to something, I need to apply a force to it, and I need to move it some sort of distance. So that's exactly what I'm going to do. I'm going to use some of my internal energy, and we're going to give this object some energy. Now, a whole bunch of you are saying, well, how am I going to give this energy? Am I just going to hold my hands around it? Am I going to squeeze on it from the sides? Am I going to lift it up? Well, now, here's the thing about giving things energy. I need to do work on them. Okay, well, the question is, how do I do work on this? I can't write exams on this thing. So what I'm going to do is I'm going to apply a force with my finger over a distance. So if I apply a force over a distance, I'm doing work. And what you'll find is that I'm fighting against gravity. So as I raise this higher and higher and higher, I'm giving this object some energy. Now, the type of energy that I've actually given it is potential. At the moment, it's not moving, so it doesn't have any kinetic. Now, it's really easy to see what happens. Now, when I release this, I'm going to release the potential energy. Now, what's going to happen is as it falls, it's going to change into kinetic and then back into potential. So I'm going to let that happen a couple of times, and I'll let you guys at home get a little bit hypnotized. So now I've got this pendulum swinging back and forth. Potential, kinetic, potential. So what's happening is as it rises, I get my maximum potential, and gravity is then going to start doing some work on this object. Just remember that gravity is always acting on an object. There we go. I've got my gravity. Now gravity is going to be the force that acts on it. So gravity changes the potential into kinetic. Work has been done, guys. Anytime there's a force and a movement in the same direction as that force, now that's the important part. Work has been done. Now you might say, okay, well, Phil, you only did work in this part. This is the work part. That's true, guys. I gave this object mechanical energy. But work is being done as this object swings. So as I swing from my maximum height, I'm going down in height. So what I'm finding is that from my one height, what I'm going to do is I'm going to ask you to figure out what's happening to the height of this as time goes by. So it's going to decrease. What's actually happening is it's coming back up to the main height, or at least the original height, and that means that it's conserved its mechanical energy. So potential up at the top turns into kinetic down at the bottom. I changed my height from my maximum height down to my lowest height. I had a vertical displacement. Now, what does that mean? Philip, what's going on here? What I'm going to find is that this object has changed its height. Now, where have I spoken about height before? Well, we took a look at the potential energy up at the top and that change in height. Where has all this energy gone? It's changed into kinetic down at the bottom. So I'm going to do this one more time. So there we go. So we've got potential, kinetic down at the bottom, potential again, kinetic, potential, kinetic. Now, all that's happening is that this object is changing potential into kinetic and back again. Each time that happens, work is going on. Now, I want you to start noticing what's actually happening to the height of this thing. No longer do I have my original height. What I'm finding is that it's going lower and lower and lower. Eventually, I've got my pendulum, which is not swinging very much at all. What's actually happened is something else has done work on my object. It's taken energy away. I want you to start thinking about that while I walk over to my board. How's the page looking, Kat?
It's looking really, really good, Phil. I think people are really understanding and enjoying.
Okay, very nice. Well, just to keep things fresh, what I'm going to be doing is I'm going to be dealing with our really, really amazing animation. Okay, guys, once again, PHET. Just Google it. It should be the first link which comes up. And what I've done is I've gone to a simulation called Energy Skate Park. So here it is. So Energy Skate Park is literally just a real example of how a pendulum might be made. I can give my skater potential energy, and that's what this blue bubble means. So if I raise him up, I do work on him with my finger over there, and what I've done is I've given him potential energy. So the best way to use this potential energy is not to drop our poor skater, but to allow him to go onto our slope and change into kinetic. So I want you to watch. As he goes from left to right, we're changing from potential to kinetic and back to potential again. Now, a lot of you are saying, this is not a very realistic situation. The skater won't go forever, and neither has my pendulum. In fact, it's almost stopped. So what we can actually start to do is we can start to introduce track friction. So there's a button over there where we can introduce the coefficient of friction. Now, Matrix, you may not have done the coefficient of friction, but just suffice to say that the coefficient of friction brings friction into the picture. So what I'm going to do is I'm going to add a little bit of friction into the situation and see what happens to our skater's energy. So there we go. I'm going to add a little bit of friction. What you'll start to notice is that there's a new piece of our pie chart. The internal energy is the pie chart, guys. It's being divided up into different ways. So what can you see is happening to the kinetic energy? Well, guys, that little green part of that pie chart is getting smaller and smaller and smaller and smaller. Guys, this is the force which stops most objects eventually. This is the force of friction. Now, there's many other forces which can stop, and what you'll find is that if you play around on your keyboard, you can actually introduce a whole bunch of really, really cool forces up to this guy. I'm not going to do it for the moment, but guys, anytime you apply a force to an object over a distance, you're doing work on it. So let's just go back to the beginning. Let's give our skater some energy. Now, the force of gravity and the force of friction are both going to do work on him. That means that we're going to get a change in the type of energy that we have. We had all potential. Watch, now I've got a whole bunch of kinetic and heat energy, which comes from the friction. Now on here, it calls it thermal energy, which is just a really fancy Greek word, which means heat. And where does the heat come from? It comes from friction, guys. Okay, so let's get into how we actually calculate these. But before we do that, I'm going to give you guys a little bit of a break. What do you think?
I think so, Phil. I think we might need one. Guys, while you play with, I'm also playing with it here, and it's really cool, I must say, Phil. Guys, jump onto your computers and check it out. Perhaps at school tomorrow, you can also let your teachers know and other classmates know. So write that site down. I've put it up on the site, on our Facebook page, so you can actually check it out right as we speak. See you just now, guys. Welcome back, Mindsetters, from that really short break. We make them short so that you guys can get back as quick as possible, because I know that you guys want to learn more. I can see the questions on your page, and I am going to hand them over to Phil when the time is right. So keep sending them through, guys. It's really awesome that you guys are actually engaging with FET sites and the Mindset site. So make sure that you guys are using them to their full potential, guys. They're really cool, and they are only out there to help you guys. So make sure that you're checking them out. Remember that site I was talking about where you can actually download notes, schedules, you can see the videos of past shows, guys. You really need to jump onto that. Download the notes right now so that you are engaging them as full talk, so that you can actually highlight and make little notes and actually improve your school notes, so that you guys can actually be the best people in your class, guys. So please make sure that you've checked that out. And in front of me right now, you are seeing the Simba Cheetos hamper, guys. It's really packed and it's really awesome. It's packed with awesome Cheeto chips and also a Mindset t-shirt. It has this Mindset lanyard, and it also has a pen and a Cheetos notepad. You guys, these are for the random acts of kindness that you guys have been doing, and you guys, I hope you have been posting them on our events wall, and you can stand a chance to win all of these. There's also 5 CDs, guys, so make sure that you are, for the month of love, for this week, guys. The month of love is ending really soon, so make sure that you are putting up those random acts of kindness on the page. I'm really looking forward to seeing them. Over to you, Phil.
Thanks so much, Kat. Well, guys, you know what to do. Guys, take the notes, download the notes, and here they are. Okay, so we started talking about work. Work is a transfer of energy from one form into another. And to do that, we needed 2 things. The one thing which we needed was a force. It could be gravity, it could be your hand, it could be friction. What else? I needed some displacement. Okay, well, it's actually really easy. All we need is a force and a displacement. And I just want to point out something. This is something that you probably haven't seen since grade 9. That the work done on an object is equal to the force parallel to the displacement. Guys, it's imperative. It's absolutely so important, guys, that you work with a force which is parallel to your displacement. Okay, but now guys, this is a grade 9 equation. Okay, it's not what you guys are going to be using. We're going to upgrade this slightly. Okay, I'm going to show you where the limitation to this equation lies. And I've emphasized it already. I need to have my force in the same direction as my displacement. And guys, it really, really seldom happens that the force is in exactly the same direction as the displacement. We're going to zip through one quick question just to get your grade 9 brains graded up to grade 12. So let's take a look at an example where we run around an example. Here we go. We've got a 5 kilogram object, and I've got a displacement of 3 meters, and I've got an applied force of 11 newtons. Guys, this is a sort of example that you would see in grade 9. Very, very simple. I've got a force, there it is. I've got my force over there, which is 11 newtons. Let's just bring this into the center of the screen so you guys can read it nicely. And I've got my displacement of 3 meters. And this is probably the simplest type of question that you'll find, is that the force and the displacement are in the same direction. Now all I need to do is to put this into my equation. I've got my force, I've got my displacement, let's plug it in, let's play. So let's play around with our equation now. So very nice and easy. We start out with my equation. Guys, please always write down your equation. Even if you don't know what to do next, say, okay, well, this is what I intend to do. The hardest part of any one of these solutions is to start the first step and say, okay, well, I know that I've got to calculate work, so let's put down an equation. Next step comes in my substitution, my 11 newtons, my 3 meters, and out comes an answer. 33 joules of work has been done on this object by the applied force. So it's probably worth noting where the work is coming from, where that energy is coming from. This is done by the force applied. Now, we're not sure what that force is yet, but we'll come along and we'll find a couple of examples a little bit later on. Okay, so that was a really simple example. I had the displacement in the same plane or level as my displacement. I had my displacement in the same plane or direction as my force. And guys, those two have to line up to use this equation. Guys, I'm telling you now, please don't use your grade 9 equation. This is too simplistic. I'm going to show you how limited it is in a moment. Okay, what happens when I've got a little bit of an angle between these two? What happens if I've got that same force applied, but now that force is being applied at an angle over there, an angle of 60 degrees to the surface? I've still got 3 meters of displacement over there. I've still got 11 newtons, which is applied to the same object. How much work is actually being done? Okay, well, this is a question I ask my grade 12s a lot. How much work is actually being done? But this is applied to mechanics. So I've now got my displacement, but here's the problem, guys. So now think about this. I've got 3 meters, but I've got 11 newtons. These guys aren't in the same direction. So what am I going to do? Well, I'm hoping that your grade 11 brain is saying, okay, well, I need to work on the same level. I need to work in the same direction. And that is one parallel to the slope. Guys, I need to make sure that I'm only working parallel to the slope. Okay, well, things are going to become unnecessarily complicated. And I'm going to show you just how complicated it gets when they're not in the same direction. Okay, so what do I do first? Well, it's quite simple. I can't use the 11 newtons anymore. What I have to do is find out how much of the 11 newtons is parallel. So in other words, I'm looking for the component. And guys, I'm looking for the adjacent side, so I hope that you know that we use cos of 60. So 11 times cos of 60 is the component that I'm looking for. Okay, so that's exactly what I'm going to do. I'm just going to find out my horizontal component, and there it is. If I substitute that in, and I find out my components of my force applied, there we go, there's my F parallel, and that's what I need for my equation, remember? This adds another step, and this, guys, this is a real pain, because you're not actually being asked vectors and components and doing all of this stuff, guys. Keep it simple, keep it smart. Now, I don't want to have to do this, because only once I've got that can I go in and then solve my full one. Okay, but there is an easier way. What I can do is I can actually shortcut all of this, and I can introduce the proper equation. And this is the equation, guys, that you should always be using. Guys, here it is. That work is equal to the force which is applied, the displacement, which we both have, so we've got 11 newtons, 3 meters, and cos of the angle between them. Now, guys, please, you're always required to use this equation. Even if there isn't an angle, I want you to think about this. What happens if they are in the same direction? Well, what's the angle between my arms? 0. I still have to use cos theta. Guys, it's a one-size-fits-all solution to all your work problems. So here we go. I've got force, I've got displacement, I've got the angle cosed in between them. Remember that cos is not a number itself, it's called an operator. It's something which I do to an angle. Okay, even if it's naught, so it may be naught, and that's what it would be in the first example. So it may be 0 in value, and that's quite important to know. So let's work with it. Let's see how we use this amazing equation. And let's start taking a look at the substitution. It's all done for us. So I know that I can substitute in, sorry, let's just keep that whole thing on there for those of you taking notes. Guys, this is already in the downloadable notes, so surf on over there. So there's my force, there's my displacement, there's the angle between those two. The 11 newtons is 60 degrees from my 3 in terms of the angle between them. So the angle between the 11 newtons and the 3 meters is 60 degrees. It's as simple as that, guys. You've just got to figure out how far apart they are. I don't have to work out any components. My life is a lot easier. And what I find is that the work done that way is 16.5 joules. Now, you could have gone and find your F parallel is 5.5 and then multiplied that by 3. And guess what? You'll get the same answer, except I have to go through 2 steps, guys, and that's a real pain. If I can do 1 step, and it's actually better to do 1 step because your examiners are looking for this equation. Every time I calculate work done by a force over a displacement, this is the one to use. This is the grade 12. This is the upgraded one. Okay, now what we're going to do is we're going to put this to work. Excuse the pun, but we're going to start with the work energy theorem. So the question is, why are we studying work and energy as separate things? If I do work on something, I give it energy. And this is where the work energy theorem actually comes in. So if I do work on an object, one of the things that I say is that, well, here's a couple of points. I'm going to let you guys read them. I'm going to put them up on the screen for you. Let's just extend that. Let's just make sure that we understand what's going on. So why the work and energy theorem? Well, here we go. When a force is applied to an object while it moves, work is done. Sorry, I'm actually moving that off your screen. Let's just highlight that. There we go. So work is done when I'm moving an object. Guys, I want to make sure that people understand that if I push on something and it doesn't move, no work is done. There's no displacement, guys. If displacement is 0, work is 0. So let's take a further look. When there is a resultant or net force on the object, that object will accelerate. Guys, this is Newton 2 stuff. This is grade 11 work. So I know that this is going to be an acceleration. Guys, please highlight it. Make sure that you know that there's going to be a change in the object's motion, a change in the object's velocity. Now here's this. This is the part which really, really ties it together. The extra force. Guys, the technical term for the extra force is force net, or your F resultant. Whichever way your teacher explained it to you, that extra force which is left over after you've added up all your forces, that extra force or net force does the work that results in a change in the object's kinetic energy. There it is. A change in the kinetic energy. So this is the thing which does the work. Work and energy. This is the work energy theorem, guys. I'm tying the two together. So the work done by the net force, so that's the extra force which I've got, is equal to the change in the object's kinetic energy. So let's see what the equation really looks like. So this work energy theorem. I've told you that the net work, so that's the total work done by the net force, or the work done by all the forces on the object, is equal to the change in the object's kinetic energy. Okay, so now, so what? I figure out that I've got work done by all these forces around the object, and that's equal to a change in the kinetic energy. How could this possibly be useful? Well, just remember that kinetic energy is a very useful way to find velocity. And that's very often where the questions go. So I'm going to try an example. I'm going to use the work energy theorem. I'm going to break it up into small pieces, make sure that everyone understands before we move on. Okay, so here it is. Here's my first example. This came from a past paper as well. It's not one of the ones which we've published, but what I've decided to do is to write it out for you. So let's use our work energy theorem. An object is pulled at an angle of 30 degrees, so there we go. We've already got an angle there to the surface with a force of 40 newtons. The frictional force experienced by the object is 12 newtons. Guys, there's now 2 forces. The object travels a distance of 3 meters under these conditions. Okay, so now let's just take a look at what the diagram looks like and where the object's going. I've just drawn in the displacement. There it is. Here's my displacement, 3 meters, my 40 newton force applied, 30 degrees up, and there, 12 newtons. Why have I drawn it in the other direction? Well, guys, friction always acts against motion. It always acts against my motion. Unless, and there are a few small cases where friction helps my motion go forward. Okay, but in terms of an object sliding over a surface by an applied force, friction is acting against me in this case. And it usually is, not always. Okay, so let's figure out what's going on here. Let's first deal with the applied force. Let's figure out how much work was done by that applied force. Okay, so here are my examples. I've got a force, I've got a displacement, I've got an angle between them. That's everything that I need. So there we go. I've got force applied, my displacement, and cos of the angle between them. So let's plug that into the calculator, and what do I find is that there is work done by the applied force equaling 103.92 joules. Now I just want to point out that it's quite significant that that comes out to be a positive value. That means if you do positive work on an object, that means that you give the object energy. I want that to be clear. If I do work on an object, I give it energy. That is positive work. What happens if I take energy away? Now, how can I take energy away from an object? Well, if you've been playing around with your energy skate park, I hope that you can see how that skate has started losing energy. I've got a stationary pendulum over here. Something took away the object's energy. And very often that is called a non-conservative force, but I don't want to get too tied up in terminology. But basically what I'm saying is that there's another force acting here which doesn't allow this object to keep on moving. There it is, my frictional force. So let's deal with the work done by the frictional force. And the equation is exactly the same. So do I have a frictional force? Well, yes, I do. I know that it's 12 newtons. Is there a displacement? Yes, I know that it's 3 meters. Now, cos of theta. Guys, this one's a little bit tricky. What I'm going to do is I'm going to put it in a different color. I'm going to take away all this other clutter. I'm going to make sure that people can see exactly what I'm doing. Guys, it's very important that you be able to get this angle correct. So let's just clean up my diagram. There we go. So nice and clean. Now that angle is probably the trickiest part to understand here. That angle is the angle between force friction and my displacement. Guys, friction is not acting in the same direction as displacement. They are directly opposed from each other. So here we go is my direction of my displacement. Friction is acting in the opposite direction. Let me see. I've got my displacement. It's half a circle away from my friction. So that is 180 degrees. So here we go. I'm going to use 180 degrees. And something really cool is going to happen. So I've got my 12 newtons. I've got my 3 meters of displacement. I've put them both in. So there we go. Tick and tick. We've taken care of them. Cos of 180. Guys, if you've got a calculator in front of you, I hope you do. Plug this in. Put in 12 times 3 times cos of 180. Close a bracket if you have to. And then press on the equals button. You say, hey, Phil, something strange came out of my calculator. What happens is that I get a negative work. I want to see what that means. So what does it mean to do negative work on something? That means to take kinetic energy away from the object. And this is why objects under friction, or friction only, will eventually slow down. Because friction takes energy away from objects. I want that to be clear. Okay, so we're moving into the last phase of our question. Now we're going to use the work energy theorem. So I figured out all the work done on the object. Let's add them all together. And then let's find the change in the object's kinetic energy. Okay, so there we go. Work net is equal to delta EK. So triangle just means change in kinetic energy. Anytime you see that triangle, guys, yes, it is Greek, okay, but it shouldn't be scary. Triangle just means change. So there we go. Work net is equal to my change in kinetic energy. My work on friction, there we go. We worked that out earlier. My work done by the applied force, all we need to do is to put in those values as positive or negative. The reason that friction was negative was because it took away energy. Work applied added energy to the object, and that was equal to the change in the object's kinetic energy. So that means that the object increased its kinetic energy by 67.92 joules. Guys, I hope that you've seen the foundation for using the work energy theorem. I'm going to jump onto an exam-style question after the break, and then work straight through it. But guys, it's in the notes. I want you to follow.
Exactly, guys. You have to download those notes. I've actually made it easy for you guys, and I've posted the fast link. So if you click on the link that I've just posted, it should take you directly to the grade 12 physical science notes for today on work and energy. Check it out, guys. I promise you it's not that hard. It's actually really, really simple. Check it out. Bye. Welcome back, Mindsetters. I hope that you guys are really enjoying this lesson. Actually, I don't hope so. I know you are. You guys have been telling me. Offense just said, this is great. Thank you, Offensive, for joining us. And make sure that you tell all your friends, guys, where it's at. Don't be stingy and hold all this information to yourself. Share it, guys. Tell them to jump onto the page. Tell them to watch TV. Tell them to jump onto the Mindset website. Give them anything that you need to give them, guys. People have also been saying that they've been helping people in their class. Of course, do that, guys. You don't want to be the only ones that pass. You want to increase everyone's pass mark. So you need to be the one that stands up, guys, and actually makes a difference. And I hope that you Mindsetters actually have those science notes just so that you can distribute them out in class tomorrow for your fellow students. Over to you, Phil.
Thanks so much, Kat. Okay, well, guys, it's straight into those exam-style questions. I've taken one from last year's Department of Education, November 2012, paper 1 question, and this is question 2. Guys, it's a really tricky multiple-choice question, and it brings into question everything that we've just done. The work-energy theorem, how do we calculate work, all of this stuff. Okay. Now, what I want you to start thinking about is this question, and let's read through it carefully. So it says a car moves up a hill. Okay. And that's pretty important because that tells me where the displacement is at a constant speed. And guys, they've capitalized this. That tells me that this object, this car, is at equilibrium. Guys, constant speed means equilibrium. That means that there is a balance of forces. So that should tell you something. Now it says, which one of the following represents the work done by the weight of the car as it moves up the hill? So now this thing, weight, just remember that weight is also called force of gravity, Fg. Guys, weight is a force which always acts in one direction, and that is down. Gravity always pulls me down. So what I want you to start thinking is the displacement in the same direction as weight, or is it against it? Is weight doing positive work, in other words, speeding up the car, or is it slowing down the car? Now, as always, if I start approaching a physics question, guys, please draw in an example there. So what we're going to do is we're going to draw in a very badly drawn car, but it doesn't need to be amazing. So there we go. So we've got our car, and our car is headed up the hill. Now let's start putting in some forces. Okay, well, my first force which I'm going to start out with is the force which is acting downwards. And that is the force of gravity. And there we go, Fg for force of gravity. Now the question is, guys, how is this car going to stay at equilibrium? Well, there's a couple of other forces, and for those of you that really listened last year, there's a force away from our surface, which is called force normal. And guys, how's it heading up the hill? Well, you're saying, well, what about the engine? Okay, so this is the force applied. Okay, now what I want to impress upon you, or make sure that I get across to you guys, is only 2 of these are actually doing work on the car. I know that the force applied, that is definitely doing work. You definitely need to do work on a car to move it up a hill. And here's why. It's because gravity is working against you, taking away your energy as you move up. It is invested as potential energy, but let's start taking a look and see if we can't figure this out from the work energy theorem. Well, before we get too mathsy, I know that there's work done by the applied force and work done by gravity on the object, and that's equal to my change in Ek. Well, what do I know? I know that this one is a positive force, plus work done by gravity, which is a negative force. Okay, now guys, I want you to be very, very careful about what's going on here. I've got an object which is not in an isolated system. Okay, it's not just a pendulum which is swinging back and forth. I've got an additional set of energy coming in from my applied force. So that's a positive force here. So I've got my negative work done on gravity. And you might be tempted to say, okay, well, negative, it's equal to delta EK. Guys, it cannot be equal to EK at all. What I'm going to do is I'm going to cancel out those two options, because the change in energy due to gravity cannot include EK. And here's the reason why. There's work done by an applied force. And my work energy theorem helped me see that. Okay, now let's start considering my change in EP. Well, did my work done by gravity increase my EP or my change in EP, or is it the negative change in EP? Well, how can I tell, guys? I've got to be very, very careful about what I'm doing here. Is it the positive change in EP, or is it the negative change in EP? And somebody online was actually asking this question. How do I relate EP with work done by gravity? Well, guys, it's actually really, really simple. Is because I've got an object which is being pulled in one direction by gravity, but its displacement is in the other direction. So what I'm finding is that if I listened earlier on, is that if my displacement is upwards, and that is my height. So remember that I got up a height in terms of this, and I've got my downward force over there, that's mg. But they're in opposite direction, guys. There's 180 between them. If my displacement and my force are in opposite directions to each other, I will have a negative change. And there it is, option D. Okay, now what we're going to do is we're going to move on to a more serious, longer question and make sure that people understand what's going on.
And they've really been asking for a challenge as well, so that'll be great.
Guys, it's coming. It's a really, really nice question. It's very unusual, and this is the reason that I've chosen it. So let's take a look at what's going on in this question. This is also adapted from the same paper, but it's a longer question, and that's question 5. Okay, so now it says, in order to measure the net force, guys, that's what they're looking for. So we're looking for the net force involved during a collision. A car is allowed to collide head-on with a flat, rigid barrier. So it's something which stops or takes away the energy from the object. The resulting crumple distance, okay, now guys, crumple distance is what you see during an accident, sadly. What happens is there's a certain part on the car which squashes or becomes flat. Now, in some of the newer vehicles especially, that's actually designed to happen. That's an energy reduction device. What it's actually happening is it's absorbing the energy of the impact, making it nice and soft. Guys, if you're inside a hard-shelled car, what happens is all the energy gets transferred directly to you, and that's a bad thing, and that's how you get injured. Crumple distances, or crumple zones, as they're sometimes called, are there to help you by reducing the energy. So now, we've got the crumple distance, which is the length by which the car becomes shorter in coming to rest. So here we go. X1 is the original length of the car. They've told us that there. So that's before the collision, and then after the collision. So the car becomes shorter. That's called my crumple distance, the distance, or at least the difference between them. Now they tell me, in one of the tests, a car of mass, look, I've got something to calculate energy with now, strikes the barrier at a speed of 20 meters per second. This car has kinetic energy, guys. It's got mass, it's got velocity, it's got everything we need for EK. All right, now let's use it. It says the crumple distance, x1 minus x2, is measured as 1,02 meters. Guys, we've got a displacement. This is all starting to work out very, very nicely. So it says ignore the effects of frictional forces during crumpling. Okay, now in real life, if you're doing these calculations, you're going to have to eventually include them. Okay, but now let's start off. They even give us the first tip. They say draw a labeled free body diagram showing all the forces acting on the car during the collision. Okay, well guys, these labels are very important, and this can be worth a lot of marks. Okay, so it says all the forces. Well, let's get the obvious ones out of the way. I've got two forces which are equal from the same point and of the same size, roughly. Now, how do we label them? Well, my force of gravity is always there. How do I properly label this? Guys, this is force of gravity on car. When I end my label, it must say the object in the end of that label. So force normal. Force normal is not a great label. So how do I describe the force of the floor pushing upwards? Well, it's going to be the floor on the object. So I'm going to say that this is actually the floor on car. All right. Now, a lot of you might be thinking, okay, well, there's a force pushing it into the wall. I know that because the object, it's going in there, there's a big smash, there's a force. Guys, that's inertia, and inertia is not a force. Inertia is not a force. I want you to remember this. I want you to wake up dreaming this, screaming this in the night. Inertia is not a force. They're going to try and trick you. There is no force pushing the car forward unless the engine is still pushing. But guys, this car just went in there with a velocity. The engine is not pushing it while it's being squashed. So there's only one force backwards from the wall. So here we go. It's a very, very large force, and this is what causes the damage. And that is my wall on the car. And that's a very large force. Guys, please make sure that your labels end in the word car. That is your object. That's where your force labels should end off. Okay, so a great free body diagram are good directions. Just make sure that the up and the down forces are relatively the same, because they are starting to look for scaling. And then this one very large force backwards, and that is the wall on the car. Guys, we're going to have to use this a little bit later, because what I want to do is I just want to impress upon you that my displacement is actually in the opposite direction to that motion. Okay, so my displacement was forward, but the force was backwards, so there's negative work being done. There we go. So now, the next one, I'm actually going to skip through this because I really want to get to the calculations. It says, state the work-energy theorem in words. Okay, well guys, basically all you've got to do is you've got to say that the work done by the net force is equal to the change in the kinetic energy. As easy as that. Guys, they will always ask you these definitions. Please learn them. Don't lose your marks because you don't know your definitions. Guys, this doesn't even take a scientific brain to remember. All you've got to do is say the equation in words and look after the keywords. They're looking for the work done by the net force, or the net work done on an object is equal to the total change in the object's kinetic energy. So there we go. A lot of technical terms, but put them in the right order and I get my marks. Here's where the fun starts. Now we're going to start doing a little bit of science. It says that assume that the net force is constant during the crumpling. And that's quite important. It says, use the work-energy theorem to calculate the magnitude of the net force exerted on the car as it is brought to rest during the crumpling. Okay, so that's quite important. Let's just see. So first of all, they want to see the work-energy theorem. Guys, don't jump into your own theories. They want to see this equation. They want to make sure that you've actually used it. So let's put it down. And then it says, calculate the magnitude of the net force exerted as it is brought to rest. There we go. That's the important piece that I'm looking for. So let's listen to them. Let's use the work-energy theorem. Okay, so my work-energy theorem says that work done by the net force is equal to the change in its kinetic energy. That wasn't too difficult. Now, what I've got to do is I've got to get quite clever. I've got to realize that work net is just another type of work. Work net is equal to F net multiplied by my displacement. Remember, guys, I gave this to you. Cos of the angle between those two, and then my change in kinetic energy. Now, anytime you see a triangle, that means a change. So it's my initial and my final subtracted. So I say final minus initial. There we go. Minus a half times m times v initial squared. I know that looks like a huge mouthful, but guys, it really, really is quite simple. What I'm going to say is that my work net, there we go, F delta x cos of theta. And then, here we go. So let's just link this up. So I've got my final minus my initial. So that is my change in my kinetic energy. I have all this information, guys. I'm looking for my F net. I have my displacement. I've got the angle between them if I'm clever. I have the mass. I have the two velocities, the final and the initial. Guys, this really is not hard now. So let's substitute. Let's find out what we get. Guys, the work-energy theorem really is this easy. So let's find out what we get for F net. So F net is my unknown. We leave it alone. Now here's my displacement of 1,02 meters. And now, cos. Remember, guys, I told you that the displacement and the F net were in opposite directions. F net was away from the wall. Displacement was towards the wall. So this will be cos of 180. Okay? Now, I'm going to take a bit of a shortcut, which your examiners like to see. They want to know that the final kinetic energy is 0. Now, you can't just leave it out, guys. you've got to put a 0. You've got to show your examiners that you know that the final kinetic energy will be equal to 0. And you're saying, Phil, why didn't you show me the mass substitution? Well, 0 squared is 0, times any mass is still 0. Here's where the interesting part lies. What I'm going to do is I'm going to say a half times by my mass of 1,200 kilograms times by my initial velocity. So let's go back to my question and let's see what my initial velocity was. It's been such a long time. So there we go. We've got my displacement, got my velocity, my mass. There's all the important information. Okay? Now let's take a look at what's going on. So my initial velocity there was 20 squared. So let's drag out the calculator and let's find out what all of this is together. Let's just make that nice and clear. I saw some other calculations going on there. Let's look at the right-hand side of my equation first. So I'm going to say negative a half. So there we go. So negative a half. This calculator is amazing. All right, there we go. Negative a half multiplied by 1200, and then multiplied by 20. Don't forget the squared. Please, guys, a lot of people forgetting the squared. And that tells me that I've got a negative change in kinetic energy. Now you might say, whoa, it's in scientific notation. Please don't stress. That's perfectly fine. Now what I've got to do is I've got to manipulate all of this. I've got to bring across the other side of the equation. I've got to divide it by 1,02. I've got to divide it by cos of 180. So let's divide my answer by 1,02 times by cos of 180. And there we have it. I've got a negative force here. So this force over here, I've considered forward to be my positive direction. So over here, this is the force which is going to stop my object. 2,35 times 10 to the 5. So there we go. 2,35 times 10 to the power of 5. That's a very big force, and this is why accidents are so dangerous. This is the net force on the object. Now, guys, also remember that force is a vector, and I've got to give this one direction. So I'm going to say away from the wall. And what I want to impress on you guys is please, please, and here's this thing which a lot of people skip out, is this work energy theorem over here. I've got to state it in the beginning before I start breaking it up into other bits and pieces. I broke this up into F, delta X, cos theta. Guys, I need to see the work energy theorem stated as an equation. Guys, if you do that, there we go. We're on our trip to getting your marks. Guys, make sure that you do exactly what they say. If you start inventing your own theories, I've seen the marking guidelines, they will deduct marks every single time. But luckily, they don't have to. Follow the steps, you'll be fine. Guys, matrix, I think that's time. Sadly.
Yeah, well, you have a minute to say something extra just for
fantastic. Okay, well, guys, what I'm going to do is I'm just going to go back and just show. I know that I'm going to get questions about this whole angle thing. Okay, now just remember that my displacement was forwards. But the only way that you can stop a car going forwards is to exert a force backwards. So, guys, there's the angle. That's where the 180 came from, and I know that I'm going to get questions from there. But guys, with that, adios.
Thank you very much, Phil. Thank you, Mindsetters, for joining us. I know that you guys had a productive lesson. You have been saying so on the page. Please continue to chat to each other, to help each other, to share notes with each other, perhaps. And if you need help, remember just to shout it out on the page, guys. It's always here for you guys to work with, rather, as we've been doing work today. Thank you to Phil for an awesome lesson. Thank you, Mindsetters. Same time, same place next week. Thank you to Macmillan. Bye-bye.
Of grade 10. So here we go. We're talking about potential energy and kinetic energy. So those are the two types of energy which an object can have in terms of mechanical energy. We're going to take a look at that guy skating on his skateboard in a moment, and we're going to try link it up with a pendulum, which I've got linked up here in the studio, and we're going to try see how mechanical energy actually works. Now, here's the thing that I want you to focus on. We need to learn that work is the transfer of energy from one form into another. There we go. So transfer of energy. And that, in fact, is the definition for work. Guys, I need you to know what it is before we start working with it. Excuse the pun. So we've got equations to describe work and energy. Well, some of those will be old, some of them will be new. I want you to work with me, work slowly, work through the stuff. And guys, work and energy is actually such a great section once you understand how to work with it. Okay, so it says use work and energy concepts to solve exam time problems. Guys, I want to get to this as quickly as possible. A lot of you guys are requesting and you're saying, Phil, for free, and I want you to surf over here and start playing around with the energy skate park. Okay, but now before we get too tied up and this guy busy enjoying himself skating, let's get down to business. Let's start taking a look at today's topic, and that is work and energy. Okay, well, most of you guys have done a little bit of energy, and remember your energy from grade 10. So we're going to focus a little bit less on the energy and a little bit more on the work, and then eventually at the end we're going to link them up with the work-energy theorem. So now all this is good and well, but guys, if you've really cottoned onto this idea, notes, guys, they're on the page, and the really nice thing about this is that most of the examples which I'm going to be working through are in the notes. You don't have to scribble and go mad making your own notes. Guys, they're available, they're for free, they're on the web. Okay, so here we go, work and energy. Let's take a look at what's up today. Okay, well, there's a couple of things that I want to make sure that people understand. Okay, we want to make sure that we know that objects have got potential energy as a result of position, and kinetic energy as a result of motion. Guys, that's a little bit of revision.
Hello guys, welcome to Learn Extra Live. You grade 12s have all been waiting for this. It's finally your turn, and today we're doing physical science with Phil, guys. It's going to be such an amazing show. As you know, I'm Katleho, and guys, I need you guys to chat to me today. I need you guys to say all you need to say and ask as many questions as you need to ask on our Facebook page. That's facebook.com/learnextra, and our Twitter handle is @learnextra. These are the platforms for you guys to basically just engage with us, guys. Engage with Phil today. Today, Phil, do you want to let us know what we'll be doing there?
Absolutely, Kat. Well, today we're going to be taking a look at work and energy, and as you can see on the screen behind me, we're going to be doing some more virtual practice.
Awesome.
I'm going to be showing you some swinging pendulums.
Awesome,
So,
Phil.
okay.
Awesome, guys. So you guys know what to do. You know Phil's virtual...
Please help me with exam type questions. So, work and energy. Now, in terms of the work-energy theorem, guys, matric, that's the new stuff. That's where we're focusing our attention today. All right, let's jump straight into this. Let's start taking a look at some of the types of energy that an object can actually have. So I'm holding this pen, I've got a pendulum over here, I'm a human body over here. All of us have internal energy. I just want to start picturing the types of energy which can actually take place in a body. So I've just drawn up a brief flow diagram. And guys, please don't scurry to write this all down. I just want to plant a picture inside your brains and say, okay, well, an object can possess energy. So I've got energy, you've got energy. We ate food this morning to make that this way. So I gave myself some internal energy. Now that internal energy can go multiple ways. Well, I know that you guys have got a little bit of a temperature, or at least a pulse. I'm hoping you guys do. Okay, otherwise you're dead. But heat and chemical is where most of our energy actually goes into. So I eat up this food and it gets stored as chemical potential energy. Any of the
Little thingies are really awesome. So if your friends aren't on the page yet or aren't watching yet, please give them a shout and tell them that Learn Extra Live is now on with physical science, and we need you guys to join us. Thank you to Macmillan for bringing us such an amazing show, guys. We really enjoy being here as much as you guys enjoy being here. So please make sure today is one of the best physical science lessons for you guys. I know you guys need it, and I know you guys have questions. So send them to me right this moment. Over to you, Phil.
Thanks so much, Kat. Well, as you can see behind me, we're going to be using one of the PhET simulations. Kat's going to be posting up one of the simulation websites, and you guys, I want you to surf over here. If you've got a PC in front of you, please, guys, I want you playing around with this. I want you fiddling around with this particular simulation. This one is called Energy Skate Park. Okay, so guys, Google PhET, P-H-E-T, so phet.colorado.edu. And these guys have made these amazing apps, and they're just for free, guys. They are up there.